Hey everybody, this is going to be our first lesson for our intro calc guys. Actually, I'm going to maybe make this a little more that way. There we go. So this will be our first lesson for our intro calc guys actually in the calculus course. We started the course with a little unit on grade 11 and 12 review topics. And now we're ready to start something that hopefully might be new to everybody. And the first lesson is called Secants, Tangents, and the Rate of Change. So if I go a little faster, feel free to pause the video or slow it down if you're taking notes. But I will try to keep it as brief as I can, but this will be kind of a big lesson, and I'll probably do it in a kind of 2 video parts. First, we have a couple of definitions to make. A secant line is a line that passes through 2 points on a curve. So let me just quickly sketch a curve for you here, or even better, I'll just have one printed for me. So a secant line is any line that if I draw it through the curve, and in this case the curve is a circle, it will actually exactly, for a circle it'll exactly hit it twice. You know, now that I think about it, a secant line is a line that passes through, I should probably say, at least 2 points. For a circle it will, because it's a straight line, exactly hit 2 points. For those of you who have said, hey, isn't that what you call a chord? No, it's actually only a chord if the end points of the line are on the circle. The fact that this line keeps going is what makes it called a secant line. Okay, now it doesn't have to be a circle. This could be any kind of curve. Here's a cubic curve. So a secant, for example, could be, say, something between when x is 1 and x is, I don't know, is that 3? So here we go. That would be a secant line right there. That would be a secant line because we hit it twice. As I was saying, it actually, you could hit it more than twice. Like you could draw a secant line this way that actually hits it 1, 2, 3 times. But at least twice means it's a secant line. Okay, so there's our first definition, a secant line. Next, a tangent line is a line that intersects, a curve at exactly 1 point. So back to my circle, a tangent line would be a line that exactly touches a circle only once. And this is actually kind of hard to draw accurately, but something like that, where it just touches it right there. Actually, you know you've drawn a tangent accurately if, when you make a perpendicular bisector to it, in other words, you make a right angle right at the tangent point, you would actually pass right through the center of the circle. Just kind of guessing that's where center is, but if I drew a true tangent, tangents are always right angled to radius or diameter lines. Now that's true for a circle. On our cubic curve, or any old kind of polynomial curve, a tangent line can really be anywhere. Like here, for the point at x is -2, I don't know, might look, oops, oh my, I'm trying to draw on not a flat surface. Let me try that again. It might be something like this, could be my tangent line, where it exactly touches it once. Even if you zoomed in microscopically, it would not look like it's crossing it twice. It only crosses it once. Maybe for this point here, the tangent line up at the top here, this would be a very steep tangent line. So something, I don't know, like that maybe would make the tangent line, put arrows at the end. And of course, here in the middle, the tangent line would actually have a slope of 0, right? Because it's kind of going that way. And that brings us to kind of our next point. I brought up the magic M word. Let's recall, the slope of the line, or of our line, is the ratio, what you used to call change in y position. I just said f of x there. I hope you realize f of x and y are kind of interchangeable in the language of polynomial algebra and calculus. Change in y position divided by change in x position. Some people would call that delta y over delta x. Delta is a symbol that means change in math, physics, chemistry. And I could also say it's delta f of x over delta x. And of course, there's the old formula that you learned for slope from way back in grade 10. So slope is y2 minus y1 over x2 minus x1. And we can also call that, of course, the rate of change of a line, because that's the change in how high it goes up and down and the change in how far it goes back and forth. The rate of change of a line is its slope. And we'll be kind of referring to this formula quite a bit, but we'll probably do it more in function notation, so it'll look a little different. But anyway, that's the basic three ideas that we're going to start with here. The secant lines, tangent lines, and slopes. The slope of a secant to a curve is what we call an average rate of change. And the slope of a tangent to a curve is an instantaneous rate of change. First, let me show you what I mean on... well, actually, why don't we first of all talk about maybe grade 10 science, and specifically grade 10 physics. Everybody who's taking, I know not everybody in this course takes grade 11 physics, but I think everybody did a unit of physics in grade 10, and hopefully you all remember these things. Remember position time graphs? So what's happening from here to here is that you have a constant slope. And let's see, what would that slope be? It would be y2, which is, looks like it's 6, minus y1, which was 0, if I take this point and this point as y2 and y1, and divided by x2, which is 3, over x1, which is 0. So I have a slope of 6 over 3, which is a slope of 2. So therefore, I can say that, remember that the slope of a position time graph is my velocity. My average velocity from points from 0 seconds to 3 seconds is 2 meters per second, right? Because meters is on top and seconds is on the bottom. Remember that stuff? Okay. Remember, what would the actual slope of this part of the journey be? Well, that slope is 0, so that means there is no velocity. That means that this person was going at a constant speed for 3 seconds, then they stopped, because that's a slope of 0. Then they have a negative slope, right? Which means that they went backwards. And then they stopped again. So I can find the negative slope. Now here's the thing about this. Actually, I have more than one of these pictures. Since I wrote all over this, so I'm going to break out another one. There we go. In the real world, of course, not every velocity is a nice straight constant line. For example, you could have a position time graph where the velocity would look like this, or the position time graph would look like this, something like that. Now what? Hopefully everybody remembers that a curve on a position time graph means that I gave away what I was going to say, that velocity changes over time at not a constant rate. So this is a constant speed, this is a changing speed, so this would be an acceleration. In fact, this is actually going to be a deceleration because it's curving downward. I'm really going faster. I'm gaining lots of speed here, and then I'm slowly kind of slowing down. Eventually, I might stop, right, at this point. That'd be an instantaneous stop. And then now I'm heading back to where I started from. This could be some sort of projectile. If I was drawing it a little more smoothly, it would be a parabola. And that's the way most physics problems in the real world actually look. They tend to be curves. So if I wanted to know something like, well, what's the average velocity from, again, we'll take the same thing, from 0 to 3 seconds. Well, now it's a curve. How do I find the slope of this curved line? Well, what I can do is I can approximate it. Note that the average rate of change is the slope of the secant line. If I were to draw a line from here to here, I could say that the average velocity is whatever the slope of that line is, which looks to me like it's about 4.5 divided by 3, which would be, what's 4.5 divided by 3? I want to say 1.5. So there we go, about 1.5 meters per second. But that's just an average. It's kind of an approximation for the whole thing. At some points it was going quite a bit faster than that, and at some points it was going slower. So that's not a great or accurate way to do things, to just secant our way through life. So note that the average rate of change is called the slope of the secant line. And the average rate of change involves finding the slope between the 2 points where the secant intersects the curve. Here's just a general curve that I sketched. Take a second if you're making notes here to just sketch that curve. And we'll call the two places that I'm concerned about point A and point B. So this would be the point where the x-coordinate is A, and the y-coordinate would be, well, I'd have to run the A value for x in through the formula. So I'm going to call this, I don't know what the formula is. Actually, I kind of do. Well, I could make up a formula that made this curve. In fact, I did. I'll show you the graph in a second. But I can call this A comma f of A, right? Again, that's really like saying x and y, or if you like, x1 and y1. Then this point here has an x-coordinate of B, and then its y-coordinate would be f of B, or again, x2, y2. So the slope of the secant between points A and B, so the slope, or the average rate of change of this curve from A to B, would be, well, I'll use y2 minus y1, but I'll use my function notation. F of B minus f of A all over B minus A. So that's still just the slope formula. I'm just using different symbols than you're used to seeing. Essentially, I'm using function notation. Now, like I said, this might not be the most accurate way to represent change of slope or rate of change, especially if now, let's suppose we wanted to know as exactly as possible what the rate of change of this curve is at the point labeled A. Imagine that you keep moving point B. Let me move up here. Imagine that you keep moving point B closer to point A. Notice that your secant line will get closer and closer to becoming a tangent line and an instantaneous rate of speed, or rate of change. So I'll give you a sec to catch up to that note. And of course, if I'm going too fast, feel free to pause if you're writing the notes down. I'll try not to be too wordy with what I make you write down when we do these notes. After all, this course is more about doing math than writing words. But in our first couple of lessons, we do have a lot of things to sort of define. Okay, caught up to me? So go back to the picture now. You kind of have to use your imagination a little bit. Imagine if I move this B point closer. Now, I have actually a smaller slope. This slope was kind of bigger, now it's smaller. And then imagine that I get it closer again, and closer again, and closer again. Eventually I'll get it so close that I can't even see the space between the dots. Obviously I can't be right at this place. Obviously B can't be right where A is. The distance between them can't be 0. How come? Well, because if B and A were at the same place, B and A would have the same value in this formula, and B minus A would then be 0. And remember that rule from math, you can't ever divide by 0. We're going to run into that a lot this year. So, and that would make sense because then my tangent line would have a slope of 0 because it would be horizontal. I don't want that, right? I know that there is a rate of change happening here, and I know it's not 0, right? I mean, if this was right at the bottom of a cusp, I guess it could be 0, but I tried to draw this so that it was a little bit going up. And then I actually decided to make myself a Desmos graph for it. Oops, not that one. This one. So that's roughly what we were just looking at. And as you can see, I can take B and I can get it closer and closer and closer and closer to A. And if you want to see, I actually have it worked out so that you can see the slope. Don't worry about all the other equations here. I'll show you how I made those in a few minutes. I won't show you how I made this curve. That you'll have to learn later in the course. But here is my new version of the slope formula. Right? So notice what's happening to this slope as I move B closer and closer. As I get closer, it gets smaller and smaller and smaller and smaller and smaller until I get really, really close. But notice I stopped changing a whole lot. I'm getting closer and closer to some value, 3.7 something. Now, A is actually 2. So right now B is 2.036. So there's a little bit of space. This is some tiny decimal. I can keep making this even smaller. I can actually enter things here by hand. I can go 0.01. And look at that. It looks like I'm very close now to 3.5. Eventually, I could even put more zeros, and I'm even closer to 3.5. Eventually, you will fool Desmos. Desmos does have limits to how well it can compute things. I think if you just keep on trying zeros, I mean, look at how close we're getting to 3.5. I think we can say with a fair amount of confidence that the slope at exactly the point A is going to be 3.5. Now, eventually, I'll fool Desmos, and it'll start giving me nonsense if I keep entering stuff. See, now it's getting bigger again. Now it went nuts. Yeah. And then, finally, it says undefined. In other words, A and B are so close together that the computer thinks that they're the same spot, which means that B minus A is 0. If I had, in fact, just entered 2, same thing would have happened. It would have said, well, 2 minus 2 is 0, and I can't divide by 0, so it's undefined. So, sliding B back. Oops, now I'm sliding A around. Sliding B back up. That's a very clearly a secant line, and it has a slope, and that slope gets closer and closer and closer and closer to 3.5. And once I'm pretty much at 3.5, well, I'm undefined there. So again, let's see if I can. Oh, my A, that's a problem. My A is not exactly 2 anymore. Let me fix that. There you go. A is 2. So my slope is very, very close to. My B is actually further over than my A. That's okay. Approach A from either side, and you should still get closer and closer to that 3.5. See, we're getting closer and closer to 3.5 from the other direction. And now, B and A are so close that this might as well be what we call a tangent line. Okay, I actually happen to know that 3.5 is the exact answer I'd get, and if you're wondering how do I know that, well, later in this course you will learn a calculus method that'll give us that exact number. But for right now, we're using kind of a geometry method. This is like a geometry solution to this problem of what is the rate of change of this curve at this point. Hey, remember back in grade 10, the first way we taught you to solve 2 equations and 2 unknowns was to do it on a graph. That's kind of the same approach here. We want you to understand it visually before we get you into the heavy algebra part of the course. Okay, back to my notes page here. So hopefully everybody finished to the end of there. So imagine that you keep moving a point B closer and closer to A. Notice that your secant line gets closer and closer to becoming a tangent, and then that tangent is what you call the instantaneous rate of change. Now, only one more page of writing words, I promise. Then we can do some mathy stuff. If, when you keep calculating the slopes as the points get closer and closer, the slopes appear to approach a limiting value, and the one we were just looking at, it seemed to get closer and closer to 3.5, whether I came at it from the left or the right. That value approximates the instantaneous change of the function at that point. So that is an important idea, that we have a limiting value. The smaller I make the distance between the points of my secant line, the closer I seem to get to this single value that's like I'm racing towards that value. And that value is called the limiting value. Let's do an actual example together. Example 1. Find the rate that x is changing in the function f of x equals x squared minus 3x minus 4 when x is 1. This is the same as if I'd have asked the question this way. What is the slope of f of x equals x squared minus 3x minus 4 at the point where x is 1? It's the same question exactly, just worded differently. So I'm looking for the slope of a curve. This is one of the things Sir Isaac Newton was trying to solve when he invented calculus. Of course, Gottfried Leibniz had pretty much already invented it and had already been working out problems with it, but the Germans and the English didn't exactly share stuff too much in those days, and Newton was not exactly a great collaborator with anybody. So Newton tends to get the credit for inventing calculus because he published his work first, but Leibniz had been working on it a lot longer, and his work was actually superior to Newton's in every way, especially when it came to notation. But don't try to tell the British that. So anyway, f of x equals x squared minus 3x minus 4. Does that look familiar? Should. It's a parabola, right? So we're looking at a parabola. Okay, what are we going to do with this parabola? Well, you know what the first thing we have to do is, if we know x is 1, we have to find a y coordinate, right? We want a point on this graph where x is 1. Well, I need to know the y coordinate of that point. So I guess the first thing I should figure out is what f of 1 is. So f of 1 is 1 squared minus 3 times 1 minus 4, which is 1 minus 3 minus 4, which is 1 minus 3 is negative 2 minus 4 is negative 6. So in other words, I am trying to find, so I'm looking for the slope at the point 1, negative 6. So that's our first kind of thought process. So now, you can make a quick sketch of this if you wanted. I mean, you should be able to, I think this even factors, right? Let's see. If I take that and I go, what two numbers times to make negative 4 and add to make negative 3? Don't I get, you can just do this on scrap paper if you want to hear. In fact, I will. I'll do this on scrap paper. Let's see. When y is 0, when I get x squared minus 3x minus 4, so 0 would equal x minus 4x plus 1. Double checking my mental math. So I have zeros at minus 4. Yee. Sorry. My day kind of got away from me, and I'm doing this video much later than I intended to. You guys can probably see on my screen what time it is. See? Didn't I tell you to not do work this late at night? Don't do what I do what I say. X equals negative 1 is my other. So there's my zeros. So let's put those down. So at negative 1 I got a 0, and 1, 2, 3, 4 I got a 0. I can find the vertex of this thing. I think we did this with some of the students in one of my classes the other day. Let's find the vertex of this thing. Remember, you can find the vertex with the little formula negative b over 2a. That's the x coordinate of the vertex. So that'd be negative negative 3 over 2 times 1. And then plug that through the formula, and you get, so f of 3 halves would be 9 fourths minus 3 over 2 times negative 3 is negative 9 halves minus 4. So that would be 9 fourths minus 18 fourths minus 4, which is 9 fourths minus, oh sorry, let's do the first two, Eesh. 9 minus 18 is negative 9 fourths, minus 4, so that'd be minus 16 fourths. So I'm looking at negative 27 fourths. Okay, so what are those two numbers? This is 1.5. This is negative 6 3/4. So 1.5, and then negative 6 3. So way down here someplace. Good enough. 1, 2, 3, 4, 5, 6 3/4. Further down. Make a bigger dot. Good enough. There we go. There's our parabola. So our parabola looks like this. Oh, I could find the y-intercept too. It should be negative 1, 2, 3. Oh, I missed it. Negative 4, right? Negative 4 is y-intercept. There we go. We know all kinds of stuff about this parabola because we did grade 11 math where we did like a month of parabolas. So now I want the slope at the point 1, negative 6. So right about there, I guess. I would like to know the slope of that, 1, negative 6. Obviously, it's going to be a negative slope, right? Because the tangent line at that spot is definitely going down. So how am I going to find it? Well, I'm going to imagine that I'm going to call, I guess I can call this point here A if you like. Call that A, right? And it's A, f of A, which I know it's actually 1, negative 6. I don't have to call it A and f of A. I know those numbers. But I'm going to imagine another point on the curve. I could even start over here maybe. Maybe I'll start at 2. So point B will have a 2 and then f of 2. And then I'll find the slope between them. And then I'll find the slope if I move it closer and closer. So in other words, I'm going to basically make a chart. I'm going to find the slope over and over again. I'm going to set one coordinate as 1, negative 6. The other coordinates are going to depend on how close I want to get. And I'm going to see if there's a pattern in the slopes as I get closer and closer. So first of all, let's try a slope where the other point is where x is 2. So if x is 2, I guess the first thing I have to do is find f of 2. I guess I should write the actual function down so that I remember what the heck it is. What is it again? X squared minus 3x minus 4. Okay, you guys better watch my mental math here. 4 minus 6 is negative 2, right? Negative 2 minus 4 is negative 6. So now my slope. So that's going to be negative 6 minus negative 6. Oh, that's going to be a slope of 0. Actually, that kind of makes sense looking at my picture that I drew here, because it kind of makes sense that point A and the 2 are kind of right across. Actually, I don't know why I put 2 on the straight line. That was dumb. Sorry. Oh, hang on. Sorry, I'm writing off the screen. This is not where B is. B is here. There it was 2, and I just found out that that's also the same height of negative 6. So there's the first B. Well, that's a straight line across. So yeah, that's going to have a slope of 0. So I'm going to move closer. I'm going to move over to 1.5. Here's where I think I'm going to grab my calculator, especially since it's late and I'm tired. I just goofed up my little diagram. In fact, what am I doing with that sad little diagram? Let's break out Desmos. Okay, Desmos. If you've never used Desmos before, here's how you use it. It's very easy. So we are making the equation f of x, and I'm just typing very normally here, is equal to x squared. To get up there, I hit shift 6, then I hit the cursor over. If you don't like finding shift 6, you can always find x squared right here. So x squared minus 3x minus 4. So I have a point. Let's put that point down. Let's call that point again. Let's call it A, and or actually, I'll just draw the point. The point was, what was it again? It was 1 comma negative 6, and I'm going to label that, and I'm going to call it point A. There it is, point A. So when I first tried the point when x is 2, and notice if I'm going to use Desmos, I don't even have to calculate the y coordinate. It'll do it for me. F of 2. See, look at that. It tells me it's negative 6. And I can actually make a point where I say I would like the point 2 comma f of 2. And it knows that that is 2, negative 6. And you can see, yeah, what's the slope of the line that joins those two things? Well, it's going to be 0. In fact, I can find that slope. I won't do that just yet, though. I'm going to finish on paper first. So back to paper. So now, first thing I got to do here is find f of 1.5, which is, let's see, what is f of 1.5? So that's going to be 1.5 squared. I guess I could put that so you can see what I'm button punching here, right? 1.5 squared. Remember, I'm using this formula. Minus 3 times 1.5 minus 4. Boom! Oh, do I really want a fraction? Let's go to decimals. Negative 6 1/4. Okay. So that's my new y2. Now I have to find the slope where that's y2. Okay, so this is going to be kind of a drag. So it's going to be open a bracket, negative 6.25 minus, remember the y1 is always going to be 6, so it's actually going to be minus 6. I guess I should just back up and make that plus 6. Oh, now I got to delete stuff. Delete. Not used to this calculator, sorry. Plus 6, close bracket, divided by, and now x2 is 1.5 minus 1, right? Because remember, x1 is 1. I could even just replace this formula with plus 6. Here, let's do that. M is always going to be my y2 plus 6 over my x2 minus 1. So that's going to be divided by, just making sure I'm punching it right, open a bracket, 1.5 minus 1. And when I close brackets, there's what I get. I get negative 1/2, so negative 0.5. So let's look at the picture. Does that make sense? Looking at the picture, if I have instead of my new point, my green point there being 2, what if my green point is 1.5? And I want f of 1.5. Yep, makes sense that I now have a negative slope of about a half, right? If you can kind of imagine. You know what? I'm kind of done imagining. Let's actually show how we make that line. Okay, first of all, instead of saying 1.5 like this, I'm going to change this number over and over again. So I'm going to put in an a, and when you put in a new variable, when you've already got an equation with variables defined, it asks you if you want your new variable to be a slider. And in this case, I'm going to say, oh yes, please, I would like a slider. And what that slider allows me to do is change the variable's actual what's the word? Actual value. You know what? Now that I think about it, I already called this point A. I'm probably confusing you by calling it A, so I'll call it B. And yes, I want a slider for B, and I'll make that B. And I don't need a slider for A anymore. So there we go. So there's that point, and yes, I'd like to label it, and I'd like to call it point B. And right now, my B is 1, which means it's right on top of A, and I'd like to start with B being at 2. Right? That was the first point. And remember, that had a slope of 0. Let's prove that it had a slope of 0. Let's actually enter our slope formula. Our slope formula is m equals y2, which again, I've been calling this is y2, so I'm just going to put f of b, minus, and then it's going to be, in this case, well, minus negative 6. So again, I might as well just say plus 6. All over. To make something all over, you highlight it, and then you type, you can either hit divide, I think down here. Is there a divide in here? Yeah, there we go, divide. There we go. Or you could have just hit your slash on the keyboard. So FB minus 6 all over, and that'd be B minus A, but A is always 1, so I don't have to change that. So, and as you can see, yeah, the slope is 0. Now, so the slope between these 2 points, if I imagine a line going through them, is 0. Again, like I said, I'm kind of done imagining. I want to see this line. What's the equation for a straight line? Remember it from grade 10 or grade 9? Y equals mx plus b. So I'm going to make that. Y equals m, and it knows to use this m. This part's a little bit weird. Instead of just saying x, you have to link the x coordinate to the a value, the thing that I'm trying to find the instantaneous velocity at, or trying to hook it to. So I'm going to actually go x minus a. So I'm basically defining the x in this equation as a function of a. Or in this case, but a has a value, of course, so it's x minus 1. And then plus, and then instead of just a regular b, I'm actually going to take f of b. And there we go. So again, that is dependent on this point, and that's why it's really y equals mx plus b, but really it's the function of b, because the b has to run through the equation so that I know where it is. So this part's a little bit confusing. You'll get used to it, but this should make total sense. That's just the slope formula. So the slope is 0 when this b number's 2. Now, what did I actually, let's go back to my work. I've already figured out that when I move the b point closer, so now that it's 1.5, my slope should actually go down to negative 6 point, or sorry, it should go down to negative 0.5. So let's see if that happens. So if I move this point to, I can slide it. Okay, I don't have the patience for that. There. And whoops, what's going on? Why did my slope leave my line? Oh, hang on, I've got something wrong here. FB minus 1. Wonder why that's not working. F of B, F of... Okay, hang on. Oh, yes, actually, oh, that's right. I'm sorry. This has to be A. This has to be F of 1. There we go. Whoops. My bad. This has to be the A value, F of A. Oh, duh. I have to link this X to A, and I have to link the Y-intercept to A, so it has to be A. I'm sorry. My bad. So the slope of this line is negative 0.5. It did figure that part out right. And now, as you can see, I can zoom in on this if you like. There we go. As you can see, our slope is now still negative, but it's a little smaller. Notice now I can actually, if I want, even start dragging the points along. So I'm getting closer and closer and closer. Of course, the question I gave you had a chart, so let's go back to the chart. What if we move the 1.5 point even closer, and it's now 1.1? So let's run 1.1 through here. So 1.1 squared minus 3 times 1.1 minus 4. That's a y-coordinate of negative 6.09. Now let's use the slope formula with negative 6.09. So I'm going to open a bracket. This calculator has an answer button, so I'm going to go answer plus 6, close my bracket, divide by, open my bracket, and that would be, what was it again? Negative 1.1. So 1.1 minus 1. Notice how small the denominator is going to be, right? It's going to be 0.1. And there we go. That's giving me a slope of negative 0.9. Let's see if my Desmos agrees with that. And look at how much easier the calculation happens with Desmos. I just go, oh, Desmos, if I move this point B to 1.1, my slope is negative 0.9. And if I did want to know what f of b is, I'd just ask it. I'd say, hey, Desmos, what's f of b? Oh, negative 6.9, the number I just had on my chart. So when you get questions like this in the assignment, and there's a bunch of them, feel free to use Desmos. I'm actually going to show you another way you can do that in a second here too. Anyway, let's try 1.01 now, because doing all this arithmetic is just so much fun. So what's f of 1.01 going to turn out to be? Because that's the number I need here. I need the y-coordinate. So that would be 1.01 squared minus 3 times 1.01 minus 4 equals, ooh, that's an ugly fraction. Let's make it an even uglier decimal. Negative 6.099. Negative 6.0099. Okay, so I'm going to use that in my slope formula. So luckily I don't have to retype it. I can just open a bracket, hit answer, plus 6, close brackets, divide by, and what was the x I used? 1.01. 1.01 minus 1, close brackets, equals, and that will be negative 0.99. Do you see a pattern happening here? Went from 0 to negative 0.5 to negative 0.9 to negative 0.99. I'm going to go out on a limb and guess that the next one's going to be 0.999. So let's see if that's right. So let's find f of 1.001, just because I love punching buttons that much. So I am going to go, okay, that is 1.001 squared minus 3 times 1.001 minus 4, big equals negative 6.000999. So that's how much this is, negative 6.000999. That's kind of looking like a pattern too, but I don't care about that pattern. What I want is the slope. So let's see, if that's my x number, how much, or sorry, my y2 number, how much is my slope? So open a bracket. The last answer I got, plus 6, and again, I'm just using my slope formula here. Close brackets, divide by, open a bracket, and what was x again? 2 zeros. 1.001 minus 1, close brackets, equals, change it to a decimal. And yep, my prediction was right, 0.999. Notice how tedious this is? Feel free to use the technology. Desmos says that when I put a 0 in here, we get 0.99. We put another 0 in here, we get 0.999. All the button punching I just did just happened right there. And again, we can keep going. It looks to me very much like what? What conclusion can we make about the slope right at point A? As B gets closer and closer to A, we get closer and closer until it starts getting stupid to negative 1. So I am going to say that's my limiting value. So back to the notes. So the limiting value of the secant is a slope of -1. Therefore, the rate of change of x of f of x at x equals 1 is -1. Or another way to put it is, or the slope of f of x at x equals 1 is equal to -1. There we go. So that is your first kind of grown-up secant problem. We'll do a real-world example in the next video, but before I end this video, I think I'm really quickly going to show you what you can do with Excel instead. If you find this all quite confusing and you've worked with spreadsheets before, this rather tedious bunch of calculating we did here can be done quite simply in Excel. Let me show you Excel. So in Excel, let me just make the same chart we just had, right? We had an X, and you can change the font and go subscript X2, 2, and here I have Y subscript 2, and then this is slope. Okay, so what were the numbers again? I used the numbers 2, 1.5, 1.1, 1.01, and 1.001. Y2. Now, how did I get, oh, hang on, gotta move that over so you can see it all. There we go. How do I get Y2 again? Well, Y2 I found by using the formula, run it through x squared minus 3x minus 4, right? Y2 is really f of x2. So I have to use that formula. So here's how you enter formulas in Excel. If you're typing a number into a cell, you just type the number. But if you're going to tell the cell, hey, I got to calculate something, you hit an equal sign. That tells Excel, oh, I'm about to use a formula. So what is the formula? Well, I need to take this number, square it, minus 3 times it, and minus 4. Here's how I do that. I am going to take this number, which is in cell A2. So I'm going to hit A2, and yes, I think you have to use capitals when you do this. A2 squared, and again, that exponent is shift 6, minus 3 times a shift 8 on a keyboard, times, and again, the same number, x, or in this case, x2, which is in cell A2. You have to tell it where the number is you're getting, and then minus 4. And remember, we had -6 for that number? There it is, -6. Now you're thinking, well, that's kind of a drag. I got to type in this formula each time. Oh, no, you don't. All you have to do is highlight the column and hit fill down. And it knows, since you typed in on this row that you want cell A2 to run through the formula, it runs through the same formula with A3. And it runs through the same formula with A4. It automatically bumps down to the next input number to give you your output. Oh, Excel's quite smart that way. Now, how did we get slope again? Well, we used the slope formula. So again, it's a formula. And we opened a bracket and went the Y2 number, which is right here. So that's B2. Minus, oh, it was minus -6, right? So I'll just go add 6, right? And then I'll divide that by, and then it was x2, which is this number. So I'll say A2. Minus 1, right? And what did we get? Hit equals, or hit enter? Yeah, the first slope was 0. Remember that? Fill down, and there's all the slopes. So if you happen to be working and you can't get Desmos to work for you, you find it too complicated, this is actually less complicated in a way if you've ever used Excel before. And for the questions in your homework where it is these tedious kinds of questions where it's going to say stuff like, yeah, here's show what the change, or show with a secant what the change in the slope would be over all these points. It's a drag to do all that button punching with your calculator. Feel free to either use Desmos to find your answers or use Excel. Okay, that's enough for you to get started on the 1.1 assignment. Check the blog. I'll pick which questions I want you to do before I go to bed, and I'll probably put my, my blog update together. The next video will be actually exactly the same thing, but I'm going to use a real-world problem. I think I have a problem somewhere that talks about what if we threw a ball up in the air from a rooftop of a building on the moon. I think that's the one we'll use. Sorry to be so physicsy for you guys who are all chemistry bio guys, but hey, this stuff was invented to fix physics problems, so don't blame me. Dig up Newton and yell at him. All right, have a good one. Thanks for watching.